One of the things we haven't looked at in optimization yet in our lessons is when we have like a number thing to minimize or maximize. We've done a lot of like area and perimeter, and we've done different formulae, but when you're given a number problem, sometimes people get confused, but it's just as easy. Okay, so this is from exercise 14C in the textbook, the very first question. If we have to find the maximum value of xy, so we are maximizing xy, okay, given that x plus 2y equals 4. So this is our restriction. So when we were doing like the fence things, we'd be told how long the fence was. That would be our restriction, okay, and we'd be maximizing the area it could contain, that kind of thing. So this is the quantity that we want to differentiate and set equal to 0, but we've got two letters, and we use our constraint to write one letter in terms of the others. Okay, just because we always find it easier, I'm going to make y the subject here. So we start with this. We've got y is going to be 4 minus x over 2. Okay, right then, so now the thing we want to maximize is xy. Okay, so you could be thinking of doing dxy with respect to our letter which we've chosen, which is going to be x. Okay, but that looks awkward, so I think it's less confusing to call the quantity we're maximizing something. Okay, so because that's a product, I'm going to call it p. So p is xy. Alright, and now I'm going to write p in terms of one letter, so because we can replace y in terms of x, that's what we'll do. So p is x times 4 minus x over 2. So if we expand out those brackets, we're going to get 4 times x divided by 2, and we're going to get x times minus x divided by 2. Okay, there we go. So that's much more sensible. So we want to maximize the product with respect to x. So we do dp by dx is equal to 2 minus x, and that has to equal to 0. And so we're going to maximize it when x is 2, and when x is 2, y is 4 minus 2 over 2, which is 1. So we have x is 2, y is 1, will give us the biggest product. So the maximum value is 2 times 1. Okay, right, let's try another similar example. Right, so this time we want to find the maximum value of the product again, given a different restriction. So we follow the same process. So the thing that we want to maximize is this product. So I'm going to call that product is xy, and we're eventually going to find dp by dx. Okay, and here's our constraint. We're going to use that to get the relationship between x and y. So we've got y is 7 minus 3x. So that means our product is x times 7 minus 3x. Let's put that in a nice format for being able to differentiate. Okay, so to maximize the product, we differentiate the product with respect to our variable x. Okay, and we set it equal to 0, because that's what happens at a maximum. The gradient is 0. Okay, and so that gives us that x is going to be 7 over 6, and that means that we want to find the maximum value of xy. We could work out y, or we can just pop straight into our product. So 7 times 7 over 6 minus 3 times 7/6 squared. I'm definitely using my calculator for that, so I can't be bothered to do it in my head. Okay, minus 3 times 7 over 6. Oops. Oh, it doesn't like the extra bracket. There we go. So we get 49/12, and that's our answer. Okay. Right. So they're relatively straightforward, but the whole xy thing sometimes confuses people. This next one is a proof instead. So here's our question. Prove that the minimum possible value of the sum of a positive real number and its reciprocal is 2. So first of all, prove means we can't mess about, we have to get a nice thorough step-by-step answer. So we want the minimum possible value of the sum of a positive real number and its reciprocal. So we want to minimize the sum of a positive real number and its reciprocal, which is a bit of a mouthful. Okay, and we've got to show that is 2. So we don't have a separate constraint, all right? But the quantity that we want to minimize is this sum. So I'm going to call it S to make it more familiar. So we've got S is a real number plus its reciprocal. And we'll just write down it's got to be greater than 0. Okay, so this is what we're minimizing. So it's slightly easier than the last one because we don't have a second letter. So I'm going to write that in a format that's nicer for differentiating. So we want to minimize S, so we differentiate it and set that equal to 0. Okay, and then we solve that. So we've got 1 is 1 over x squared. So that gives us x squared is 1, which means x is plus or minus 1, but x is greater than 0, so then that tells us x is positive 1. Okay, now we have to prove that the minimum possible value of the sum and its reciprocal is 2. So let's just check what the sum is. So it's going to be 1 plus 1 over 1, which is 2, and we have to prove that we've got our minimum. So we need the second derivative to show that we have a minimum. So here's our first derivative. So if we differentiate that again, we're going to get positive 2x to the negative 3. And we want to check what that value is when x is 1. Okay, so if we pop that in, we get 2 over 1 cubed, which is 2, which is greater than 0. So then we must have a minimum. Okay. Right, one more problem solving type to do. Different flavour this time. Okay. So the sum of two numbers, x and y, is 6, and they're both non-negative. Okay, find the two numbers if the sum of their squares is the minimum possible, and secondly, if the sum of their squares is the maximum possible. Okay, it's just a find question, so we can do it however we like. We want to minimize the sum of their squares. Okay, so that's the quantity that we're minimizing. So let's just write down what is that quantity. We've got, we'll call it S, is equal to x squared plus y squared. Okay, so that's the thing we're minimizing. That's what we differentiate. Okay, so the sum of the squares of x and y is 6. The sum of the two numbers x and y is 6. So that's going to be our restriction. So we know that x plus y is 6. And we can use this to write one variable in terms of the other. So let's have y is 6 minus x. So now we can rewrite our sum of squares as x squared plus 6 minus x all squared. We expand that out and tidy it up. Okay, right. Now to minimize, we differentiate, set it equal to 0. So ds by dx is going to be 4x minus 12. Okay, now we set that equal to 0 and we only get one solution, which might strike you as odd because we need a minimum and a maximum. And so this is where we have to think about the graph to help us understand what's going on. Okay, so I'm getting my calculator and I'm going into graph mode and I'm typing in what S is. So 2x squared minus 12x plus 36, I've already popped it in there. With my, in my view window, I want to go, I can't go smaller than 0, but if x was 0, then that would have to mean that y was 6. Okay, and then we can have x could be anything up to 6, but we can't have more than that, or otherwise y would be negative. So we only want to go x is 0 up to 6. So that's limiting it. So if I do that, I've also made my y values going up to 40 there. Okay, so let's have a little sketch of that to see what's going on. Okay, so from 0 to 6. Right, now we have just worked out that when x is 3, we've either got a minimum or a maximum, and we can see from the graph that we have a minimum. We could do the second derivative if we wanted to. Let's just have a look at that. d2s by dx squared would just be 4, which is greater than 0, so we've definitely got a minimum there, justifying what we've seen on the graph. Right then, so if x is 3, then that would give us y is also, it's going to be 6 minus 3 is 3. So that gives us our minimum possible. So that answers part A. But we can see that we get our maximum possible from the ends. Okay, so when x is 0, so for B we could have x is 0, and in that case y would be 6, and our total would actually be, we'd end up with the sum of squares would be 36. Okay, or we could have x is 6 and y is 0. So if something odd comes up, a really good idea is to sketch on your graph. I hope that's helped.